Okay, so we started off by talking about position, velocity, and acceleration. First of all, let's think about these things as vectors. We defined acceleration to be the time rate of change of velocity. Likewise, velocity was the time rate of change of position. And position itself was basically a vector that went from the origin to our particle. And this was expressed using one of several coordinate systems. As scalars, we had acceleration is equal to dv dt, velocity is equal to ds dt, where s was basically this scalar variable that gave us our distance down the actual path the particle had traveled. By solving for dt in the expression for by solving this expression here for dt and plugging it into the above, we derived a useful variation, a ds is equal to v dv. We found this useful because it allowed us to deal with kinematic problems where time is implicit rather than explicit. Now, the next thing we did was we looked at an important special case. And this was when we had constant acceleration. And of course, constant acceleration is something that is probably at best a good assumption and certainly doesn't hold in all cases. But if we work with that assumption, we derive this family of equations. V is equal to V naught plus a constant times time. S is equal to S naught plus V naught t plus 1/2 a constant times squared. And lastly, that v squared is equal to v naught squared plus 2 a constant s minus s naught. Okay, very good. So again, the key thing is to remember that these do not hold in all cases. You have to be careful to apply them appropriately. We then talked a little bit about a numerical approach to doing kinematics. And basically, sometimes either because you have an erratic motion or because you're working with sampled data, there may be a need to deal with numbers directly, and you don't have equations to apply as we had above. In this case, basically, as you guys practiced in your homework, the point is to just use your knowledge of calculus to find slopes in the case of going, for instance, from position of velocity or velocity to acceleration, or integrals, as in going from acceleration to velocity or from velocity to position. And we then moved into the specific coordinate systems. And really there were 3 coordinate systems that we focused on. We had, first of all, so let's see, coordinate systems. we had Cartesian. With Cartesian coordinates, we were free to put our origin wherever we like, and then we could call this x, y, and z, or I, j, and k. We have a path somewhere, our particle is moving along this path, and we can point to our particle using our position vector r. So just to kind of try and make the similarity between the coordinate systems as strong as possible, let's just, for the sake of symmetry, call this ux, uy, and uz. The next coordinate system we looked at was the normal tangent coordinate system. Okay, so in this coordinate system, we had one special rule, and that was if we're interested in our particle here, we had to find in the locale of the particle the center of curvature. And then what was interesting was that the u sub n direction pointed in from the particle in towards the origin. So this here would be our u sub n. And then perpendicular to that, and therefore also tangent to the path, is our tangential direction. So u sub n points into the origin, so just again to be clear, origin we can put wherever we want. In the case of Cartesian, origin here has to be at the center of curvature, and u sub n points in, u sub t tangent to that. And lastly, and just a quick note here, this can be three-dimensional. That third dimension was called binormal, but by construction of this coordinate system, no motion and no acceleration occurs in that binormal direction. The third coordinate system in the two-dimensional case is polar, in the three-dimensional case is cylindrical. Okay, so here we again can put the origin of the coordinate system wherever we want to. We will put it over here, and the components of this coordinate system, again, kind of go from origin to particle, but one thing that can be confusing is that the radial direction points from origin to the particle. So this is my u sub r, and the perpendicular to that, or the direction that u sub r goes if the coordinate system swings by some distance theta, we call u sub theta. Now, with this coordinate system and the last one, it's often useful to be comfortable placing these vectors either on the origin or on the particle. So again, this is still my u sub r, and this is still my u sub theta. And in the case of the prior coordinate system, I can draw these out from my origin. This is my u sub n. This is my u sub t's. The basis elements themselves are three vectors, and what's really important is we know that their unit length, and we know how their orientation is defined within the coordinate system. The last thing we had to do in Chapter 12 were a few specific things, and I will go through each of those briefly in the next video segment.